limit superior and limit inferior of a function at a given point. Okay. So limit okay, what it is? So we are defining in the following way. So let's say let T be a limit point of a subset D of R. Okay, and let's say f is a function from D to R. Okay, then we are defining then the limit superior of f at C is, so we will write this way, lim 2 of f of x tends to C. Okay, it is infimum of all delta greater than 0, supremum of n dash C delta intersection D fx. What is n dash C delta? N dash C delta is a deleted neighborhood of C. That means it's a neighborhood of C, but the point C has been deleted from that neighborhood. So n dash C delta, you can think about this is like C minus delta to C union C to C plus delta. Okay. So what's going on basically? So what we are doing over here for a particular, so let's say we have a delta. So for a given delta, we are calculating the supremum of the function fx in that deleted neighborhood. Okay, and then whatever values we are getting, we are calculating. So for a given delta greater than 0, let's say we are calculating g of delta, which is supremum of fx. X belongs to, I forget to write, x belongs to n dash C delta intersection D. So we are calculating supremum of this function. Then, so now it might possible that function is unbounded in that neighborhood and you have a value is a infinity. Okay, that's possible. So it can be plus infinity. Okay, that is possible, and also can be minus infinity in that way. Okay, so anyway, so we are calculating g of delta, which is supremum of fx. X belongs to in that neighborhood. Then what we are calculating? We are calculating the infimum of all delta greater than 0, g of delta, such that, okay, delta greater than 0. So whatever values we are getting, so then we are calculating the infimum of that set. That's we are defining the lim sup of fx, okay, or limit supremum of fx. Okay, similarly, let me define, I will give, okay, first let's see an example, I mean, how it's look like for a very simple case. Okay, so let's say fx equals to x, okay, and consider our c equals to 1, say. C equals to 1, say. Okay, so if we draw the picture, here we have, let's say 0, that point, and here we have this 1 in the line. Okay, so this is a line for, let's say, y equals to fx. This is y, this is x, and here you have the point 1. Okay. So if we draw the graph of the function, it is like this. And actually, because we are all familiar with the limit, you know that limit x tends to 1, this value of the function will be equals to 1, correct? So let's say here you have a 1. Okay, so let me take this line where you have y equals to 1. Okay. So now what we are doing for a delta, so let's say for any delta, we are calculating delta minus 1, delta plus 1, okay. And we are now in this particular interval, what is the supremum of the function? So if we consider this interval and this, what is the supremum of the function where you are getting? It's a monotone function, correct? So almost over here. So it's in this case, this 1 plus delta will give you the supremum. The supremum of the function will be 1 plus delta. Okay. Now let's say I reduce the size of delta. Okay. Then what it will happen? So if I reduce the size of delta, now my new delta is like over here. So we will have next value will be over here. So if you move towards, if you reduce the size of delta over and over again, you can see that you are getting the values which is near to the value 1. Okay. So whatever you do, how many times you reduce, the infimum will be equals to 1. You cannot get an infimum which will be less than 1. Correct. So in this way, you see that lim sup actually in this case it will be equals to 1. Okay. That's the idea. So you are calculating for a given delta, you are calculating supremum of the set. Then for each delta, we are taking the infimum of all these values. Okay. Okay. Is it clear what we mean by limit supremum and how it's related to limit of a function at that particular point? Because it's a very simple example. So that's how. Okay. First, let me define limit infimum. Then you will see it clearly. Okay. So definition of limit infimum. So again, let C be a limit point of D and f from D to R be a function. Then the limit inferior of f at C is defined as, so we are using this notation, lim inf x tends to C fx. What it is? It is now supremum of delta greater than 0, infimum x belongs to n dash C delta intersection D fx. So now in this case, what we are doing, let's say for a given delta, we have a function h of delta. We are defining h of delta as infimum x belongs to the deleted neighborhood, delta deleted neighborhood of C. We are calculating this value, infimum value. Then we are taking the supremum of this set. Then this lim inf is nothing but supremum of the set h of delta such that delta greater than 0. Okay, one thing I think you have observed that g of delta, the way we define, is a monotonically increasing function, and h of delta is a monotonically decreasing function. Okay, so more you increase the value of delta, so you have the chance to get a minimum more lesser value. Okay, so anyway, that's how we are defining the limit infimum of a function. Okay, this to work with this definition is really difficult. So that's how we have some theorem that I will come to that point later. But first of all, what it is. Now again, look at this picture. Now for a given delta, we are calculating now, what we are calculating? The infimum of the set. For this 1 minus delta comma 1 by delta, what will be the infima of the set? It will be over here, correct? Now if you reduce the size of delta, then it will be over here. Again reduce the size of delta, you see that it is approaching to the point 1. Okay. So when you have the limit at that particular point, the limit supremum and limit infimum will be equal. Okay. They will give you the same value. Okay. So that is the idea of limit supremum and limit infimum of a given function. Is it clear little bit? Okay. Good. That's the idea. Okay. Here is a theorem for limit supremum, but you can similarly write a theorem for the infima counter inferior part. What is this? It says that, okay, theorem 1, let limit, okay, x tends to c, lim sup of f of x equals to L, which is a finite number. Okay, so I should write is a finite. Be finite. That means it's a real number. Okay. Then for any epsilon greater than 0. Okay. Okay, so first let me write any epsilon greater than 0, there exists a delta greater than 0 such that f of x is less than L minus epsilon for, sorry, L plus epsilon for all x belongs to n dash c delta intersection D. And second condition is that, okay, for any epsilon greater than 0 and delta greater than 0, there exists x delta belongs to n dash c delta intersection D such that f of x delta is greater than L minus epsilon. Okay. And these conditions are also sufficient. Okay. So if we have a limit and limit is a finite, then these two conditions hold, and if these two conditions hold for a particular value of L, then the lim sup will be L, and that's a finite number. Okay. Okay, let's see. I mean, we're not going to prove that much, but you can see the what is the meaning of it. Okay. So let's say we'll just say that okay, limit exists. Lim sup of fx equals to L. What is the meaning of that? How we get this first and second condition? So lim sup of fx as x moves towards c is L means what? You have infimum of delta greater than 0, supremum of x belongs to n dash c delta intersection D fx is equals to L. Okay. So now this set is equals to L. Okay. So infimum of all delta is equals to L. So L is the infimum of the set. So this is G of delta, correct? Where we have already defined what is G of delta. Okay. Where our G of delta is supremum of x belongs to n dash c delta intersection D f of x. Okay. Now this set has an infimum L. Okay. That means what? That means if you, this is a lower bound, least upper bound, greatest lower bound. So that means if you add a positive number L plus epsilon, so by that property what will happen? There will exist an element of this set, that means there will exist a delta such that, so since L is the infimum of this set, so there will exist a delta greater than 0 such that G of delta will be less than, sorry, not less than, yeah, it will be less than L plus epsilon, correct. G of delta will be less than L plus epsilon. So that means what? That means supremum of the set Fx for this particular delta, okay, let me write as delta star. Supremum of the set in that C delta star intersection D will be less than L plus epsilon. If the supremum of the set is less than epsilon, that means what? All the elements, so this means Fx less than L plus epsilon for all x belongs to n dash C delta star intersection D. Am I correct? This is by the property of infimum, because L is infimum. If you add L plus epsilon, there will be a number such that G delta star in this case it will be less than L plus epsilon. Now G delta star is nothing but supremum of the set. If the supremum of the set is L plus epsilon, that means all x in that set is less than L plus epsilon. Okay. So this is nothing but your first condition. You see that for any epsilon greater than 0, depends on the choice of epsilon, there will exist a delta such that Fx less than L plus epsilon for all x. This is the first criteria. So we prove that this will work for the first criteria. Okay. So because of that, we have this idea. Is it clear how I got, we got this point? This is because just using the concept of infimum of a set. Okay. Okay. Next part is actually easy. What is next part? So since L is the infimum of the set, so L is your infimum delta greater than 0 G of delta. That means what? That means for all delta greater than 0, G of delta is greater than equals to L. Okay. So which is greater than equals to L minus epsilon for any epsilon greater than 0. Okay. So that means what? G of delta is supremum of Fx, x belongs to n dash C delta intersection D. Clear? This is infimum. So infimum means all the G of delta should be greater than or equals to L. And greater than equals to L means it should be greater than L minus epsilon for any epsilon greater than 0. Okay. Now this is G of delta is nothing but supremum of Fx, which is greater than L minus epsilon. Now if the supremum of the set is L plus epsilon, so obviously there will exist an element. So then there exists an element x delta in this set such that f of x delta should be greater than L minus epsilon. Can you tell me why? Why it is so that there should exist an element x delta such that f of x delta should be greater than L minus epsilon if supremum minus epsilon. Think other way. So let's say for all x, it is less than equals to L minus epsilon. And then what you will get? You will get a contradiction. Okay. So because of that, you will always going to have a x delta for which f of x delta should be greater than L minus epsilon. Okay. So that's the proof of the theorem basically also. So that's the property if and only if condition. The conditions are also sufficient. Okay. So again, this is the basic structure of limit supremum. Similarly, you have the counterpart for limit infimum. You can get the theorem. We are not writing that down. Okay, but the structure you should be clear. Okay, but still it is not that much helpful to get the limit of a limit supremum or limit infimum in practice. So for that we have this following theorem. What is that theorem? Theorem says that, okay, so suppose, okay, lim sup C fx equals to L is finite. Okay. Okay. What will happen? Okay, this is finite. Consider this set A, which is collection of all m real number, such that there exists a sequence xk with xk not equals to C, and okay, so there are many conditions, many other conditions we have to add, comma xk converges to C and f of xk converges to m. So what we are taking over here, for all sequence and where xk, for all k, xk not equals to C and xk converges to C. So actually we are taking all the sequence converges to C except that sequence with some terms with C. So we are just discarding all those sequences, and then we are taking the value of the function f of xk tends to infinity. Okay. Then if that limit supremum of fx is finite, what will happen? This L will be maximum of the set A. Okay, this set will be a closed set. You can check that. So in that set, L will be the maximum of the set. So limit supremum will be. So what we will do basically, we will calculate all the possibility sequential limit of the function. Okay, so that means whatever sequence we have converges to C, we will calculate f of xk which converges to some numbers, and then we will collect all the possible value and take the greatest value. That will be the limit supremum of L. Okay, that's the idea. And also if we have this maximum of L is a finite number, then the supremum is also going to be finite and you have that value. Okay. So, and for limit infimum, what it would be? It would be just minimum of all this sequential value of the function. Okay. So we'll calculate all the possible sequential values and then take the minimum of the set, and that will be the limit of the function. Okay. What about if it is infinite? Lim sup is infinite. So here is that theorem. It says that lim sup of fx, x belongs to C, is infinity if and only if there exists a sequence xk with xk not equals to C for all k and not and basically, comma xk converges to C and f of xk converges to infinity. Okay. If f of xk converges to infinity, then limit suprema of fx is infinity. If there is at least one sequence is there for which this is true, then the lim sup of fx will be infinity. So it's very much helpful for us to get the limit suprema of a function. Okay. Okay. What about if the limit sup x tends to c, fx is minus infinity, if and only if for any sequence xk comma xk not equals to c, xk converges to c, and f of xk converges to minus infinity. Okay. If all sequence f of xk converges to minus infinity, then lim sup of fx will be minus infinity. Okay. Similarly, if you consider the infimum case, what it would be? So it will be minus infinity if and only there exists a sequence for which f of xk converges to minus infinity, and lim inf will be infinity if for all sequence f of xk converges to infinity. Okay. So just reverse the process. So this will help us to evaluate lim sup or lim inf of a function. So if we have a finite value of, if we calculate all the sequences and get a finite value, and then we'll just supremum will be the all the possible subsequential values of the functions, and maximum, and for infimum you will have the minimum. Okay. Okay, let's see some examples basically. What is the value of lim sup x tends to 0 sine 1 by x? Okay. Lim sup of x tends to 0 sine 1 by x. Yeah, it will be 1. But you have to see why. Because whatever you can have a subsequence like xn will be, you can take xn equals to 1 by n pi, this will give you 0 basically. Okay. So if xn is 1 by n pi, then f of xn will be 0 and this will converge to 0. If xn equals to 2n pi, not 2n pi, yeah. Yeah, 2n plus 1. So if we have all odd values, then it will be a 1, converges to 1. No, pi, 3 pi. No, 3 pi it will be 1 or minus 1. All sine 10, it will be minus 1. Minus 1. So, yeah, like if you consider all those values, like in the second quadrant, exactly second quadrant like pi by 2, then again multiple of pi by 2, you will have the value 1, and then again you have the odd multiple of pi by 2 will give you. So what should I write? So you got it, like for sequence when this will be, yeah, 4 it will be written. So like 5 pi by 2, then you have 9 pi by 2, and that means it is in third quadrant it is coming. Third 3 pi by 4, no, first quadrant. So this will give you f of xn is 1 converges to 1. Similarly, you can have minus 1, and because we are calculating limb soup, we will take the maximum of all possible functional value. So maximum of all possible functional value will be obviously 1. Okay, so you have only 0, 1, minus 1 type of thing. Okay, so 1. What about limb imp? So you can already have seen that limb imp of same function x tends to 0 sine 1 by x will be, it will be minus 1. Okay, so same idea. What about if we take limit x tends to 0 mod of sine 1 by x, limb soup, it will be 1. But if we take limb x tends to 0, limb imp of sine 1 by x, will it be minus 1? Now it will be 0. So that's the idea. Okay. Fine. Okay. What about this limit supremum of x tends to 0 log x? So sometime instead of looking at the sequences, you can draw the graph and find that it is easy to handle. So it's an unbounded function at the point 0. That sine 1 by x, mod of sine 1 by x, is a bounded function in the deleted neighborhood of 0. But it is unbounded function in the deleted neighborhood. Okay. So therefore, you will find that this will be nothing but minus infinity. So whatever sequence we will take, it will unbounded below. Okay. So it will be limb soup of log x will be minus infinity. Similarly, limb imp also going to be in this case is minus infinity. So actually you have limit x tends to 0, log of x is equals to minus infinity. Because in this case your limb soup and limb imp also going to be same, and you have this value. Okay. There are many sequences, but already we got the highest value 1. Because sine function cannot take a value more than 1. Similarly, you can calculate for different function. Okay. So for finite function, I mean, if you have a bounded function, it's sometimes easy to get the limit supremum, limit infimum will be easy to get. But sometimes if it's an unbounded function, you have to look at the different possibilities, and from there you have to get the maximum value or minimum value of the function. Okay, so that is the idea more or less. I did not cover all the things, but this is I think now we can discuss different type of discontinuities of a function. Okay. So types of discontinuity of a function defined over an interval. Okay. So let's say we have a interval. Okay, so interval might, like, you know that my open interval a b, closed interval a b, a to infinity, minus infinity to a. So all possibility. Okay. So let there are different possibilities. First we will consider, like, let I be an interval. So case 1 we are considering now. Let C be a left endpoint of I. So C be a left endpoint of I, and F is not continuous at C, but F is continuous at, or continuous on CD. So we have an open interval CD such that this CD open interval contain inside I. Okay. So it's not continuous at the point, but in some neighborhood of that point. So we consider in that neighborhood, in that sense. This left hand point of the I, we don't know whether f is defined at the point R C or not, but f is not continuous at the point C, but f is continuous on CD basically. Okay. Okay. So under this there are different cases. Okay. So first case is that, so under this case, this bigger case, so first we will consider C is a left hand point. Other case is that C is a right hand point. Other possibility is that C is the interior point of the interval. So three possibilities. But if we discuss the left hand point of the interval, then similar to this you can have right hand point. But for interior point we have to discuss separately. Okay. So let's say now we have this. Okay. So under this we have different cases. Okay, how to write? Let's say case number I. Okay. So limit x tends to C exists. Limit x tends to C fx exists. Okay. So this limit exists, but either f of c is not defined at the point, or this value is not equals to f of c. Okay. But either f of c not defined, or limit x tends to c f of x not equals to f of c. So this type of discontinuity is called removable discontinuity, because by suitable choice of the value of f, we can remove the discontinuity of f and we can make a new function, like we can have a new function which is exactly equals to f on I, but at the point C you have some different values. Okay, you have defined that way. So that's called removable discontinuity. Okay. So this type of discontinuity of f is called removable discontinuity of f, and C is called the point of removable discontinuity. Okay, I am not writing all this stuff, otherwise it's too lengthy. Okay, you just write it, then the C will be called the point of removable discontinuity. Okay, so I'll give an example. I think most of you are familiar with the example. It's very simple example. Fx equals to x square minus 4 by, let's say, x minus 2, when x is not equals to 2 but x is greater than 2, and let's say we are defining 5 when x equals to 2. Okay, so we have a function here f from 2 to infinity to r. Okay, so our in this case c is 2. You can clearly see that this function is not continuous at the point 2, because limit, what is the limit? X tends to fx. Limit x tends to fx is limit x tends to 2 x square minus 4 by x minus 2, and you have 4, correct? Which is obviously not equals to f of 2. So therefore, C is the point of removable discontinuity. But you can define a new function g from 2 infinity to r by the following way: gx equals to fx if x not equals to 2, and 4 if x equals to 2. So then this g is an extension of a, and this function is a continuous at the point 2. Okay. So if we have a removable discontinuity, we can extend a function, okay, to a continuous function. Fine. So it's a very simple type of discontinuity. Okay. Okay. Next is that this limit obviously does not exist. First case we assume that limit exists. Second case is that limit does not exist. Okay. But limit does not exist. There are two possibilities. Okay. So now case 2 is that let limit x tends to c fx does not exist. Okay. So under this we have two subcases. Subcase 1 is that there exists a neighborhood, tilted neighborhood of C, where f is bounded. Okay. So f is bounded on some deleted neighborhood of C. Okay. So some neighborhood is there of C where f is bounded. So in this case, we will say that function has oscillatory discontinuity. Okay. Bounded on some deleted neighborhood of C. Okay. In the interval. Okay. What do we mean by that? So that means that a mod of fx is less than or equals to m for all x belongs to n dash c delta intersection I for some delta greater than 0. Okay. So some delta exists, so a delta neighborhood of C will exist where f is a bounded function. Okay. So in that case it will be called oscillatory discontinuity. Okay. So this type of discontinuity of f is called an oscillatory discontinuity of at the point C, and C will be called the point of oscillatory discontinuity at the point C. Okay. So what is an example? We already did that example. Sine 1 by x. So example is fx equals to sine 1 by x when x is greater than 0, 0 when x is not equal. Okay, anyway, you don't have to define at that point. It might be possible that function is defined at that point or not defined. It does not matter. If we have this, does not exist, but it is bounded in some neighborhood. Okay, then we have the idea of oscillatory discontinuity, and C will be called the point of oscillatory discontinuity. Okay, I'm not writing that C is a point of oscillatory discontinuity. Okay, it's too much. So what is the other case left with us? So it's a bounded on some related neighborhood. So other case is it's a unbounded in every neighborhood. Okay. So now the third case, or not third case, sub case 2. So F is unbounded on each neighborhood. Okay, deleted neighborhood actually, or let me write okay. Oh, on each n dash delta. Okay, so each delta F is unbounded on that neighborhood of related neighborhood of C. Okay, so in this case there are two possibilities again. Okay, one possibility is that F is infinity, I mean limit is infinity. Other is okay. So where is that? Just a minute. Where is that? Yeah. So this type of discontinuity will be called infinite discontinuity, but under this we have two more possibilities. Okay. So is this type of discontinuity. Okay. So this type of discontinuity is called infinite discontinuity. At C. Okay. Now there are two possibilities under this because F is unbounded. So it might possible the limit is equals to infinity. Okay. So there are two more possibilities. One, if limit x tends to C, Fx is infinity or minus infinity. So either it is infinity or minus infinity, we are always going to say that the function has infinite discontinuity at the point C, and it will be called the point of infinite discontinuity. Okay. So this is one possibility, and C will be called the point of infinite discontinuity of F. And obviously second is that limit does not exist. Okay. Limit x tends to C, Fx is okay, the other case. So in this case it's nothing basically. Okay, so although we started with the case that limit x tends to C Fx does not exist, in the sense that it's not finite, but this case limit, it might be possible the limit x tends to c, fx is infinity or minus infinity, it will be called the point of infinite discontinuity. So other case where this is not true, so fx is neither equals to infinity or minus infinity, then C will be called a point of infinite oscillatory discontinuity. Okay. So then C will be called, okay, so a point, it should be a point of infinite oscillatory discontinuity of F. Okay. I will give you example, but first of all, let me give you a whole picture. So what is happening over here? So now we have limit x tends to c fx exists finitely. Okay. So exist finitely. So in this case, you have only removable discontinuity. Correct. And second case is that limit x tends to c fx does not exist finitely. So under this you have case where f is bounded in some delta neighborhood. So f is bounded on some n dash c delta intersection I. So what type of discontinuity we are saying? We are saying this is oscillatory discontinuity. Okay. So other case is that f is unbounded on each n dash c delta intersection I. So under this you have two possibilities. One, this limit fx is either infinity or minus infinity. Then we will have infinite discontinuity. Or point of infinite discontinuity, and this limit does not exist at all. Even the value is not infinity or minus infinity. Okay. So then we have oscillatory infinite discontinuity. Okay. So these are the possibilities when C is a left endpoint of an interval. Okay. Okay, let's see examples. Is it clear, the full picture? This is the full picture you have. Okay. If exists finitely, then removable. Does not exist finitely, then you have all these possibilities. Okay. Either it is oscillatory discontinuity, that means finite oscillatory discontinuity, better to say. And other way is that you have infinite discontinuity or infinite oscillatory discontinuity. Okay. So let's see examples. Okay. What about log x? We already discussed fx equals to log x when x greater than 0. What type of discontinuity this function has at the point x equals to 0? It's a limit. We have already learned that it is infinity. So limit, we learn that this tends to 0, fx is minus infinity. So therefore, it's a infinite discontinuity. So see, 0 is the point of, so x equals to 0, is a point of infinite discontinuity of f. Okay. What about this function? Fx equals to 1 by x sine 1 by x greater than 0, 0 x equals to 0. So all those sine x, sine 1 by x is a bounded function, but because of that term 1 by x, the function is unbounded in each related neighborhood of 0. Okay. So f is unbounded on each related neighborhood of 0. So f is unbounded on each uh, deleted neighborhood of 0, okay, in 0 to infinity. We are discussing in that interval 0 to infinity. Okay. Now, is the limit exist? Is it infinity or minus infinity? No. If you take a sequence like 1 by n pi, what is the value we are getting? Xn, if you take 1 by n pi, so we are getting f of xn as, so n pi into 0, so it's a 0 converges to 0. Okay, that's fine. Now, but if you take xn equals to 1 by 4n plus 1 pi, what is the value we are getting? It's a 4n plus 1 pi into 1. Correct. So where it is going? Infinity. Okay. As n tends to infinity, this is going infinity. Is it clear? If you put over here xn equals to 1 by 4n plus pi, so it will be 4n plus pi and sine of that will be equals to 1. So now you have 4n plus 1 pi, that moves to infinity as n tends to infinity. So you see that for different sequences f of xn is moving towards different value. So obviously that means that limit does not exist. Correct. So that limit cannot be infinity or minus infinity, because for one sequence it is moving towards 0, for another sequence it is moving towards infinity. Okay. So therefore that limit does not exist. Okay. We are not discussing limit supremum or limit infimum. That limit does not exist at all in this case. Okay. So therefore this limit, this implies that limit x tends to 0 fx not equals to infinity or minus infinity. So that means 0 is the point of infinite oscillatory discontinuity for this function. Okay. So right over here, so in this case x equals to 0 is a point of infinite oscillatory discontinuity of f. Okay. Fine. Okay. Okay. By the way, what will be the limit supremum for this function? Infinity. What will be limit infimum? No, minus infinity. Because you can take sequence of other values like negative, when sine value will be in a minus 1. Like if we have 3 pi by 2, that term 3 pi by 2, then what is 7 pi by 2 multiple that. That will give you minus infinity. So limit infimum will be minus infinity. So obviously that means it does not exist. Okay. So anyway, but 1 it is 0. So anyway, so this is another possibility. Okay. So 0 is the point of infinite oscillatory discontinuity. Okay. Now let's say similarly you can define for right endpoint of a right endpoint of an interval. Now let's say C is an interior point of an interval and discuss different type of discontinuity. Okay. So let C be an interior point of the interval I. Okay. So now we'll go one by one. So first case is that limit exists but does not equals to f of c. Okay. So first case, limit x tends to c, fx exists in the sense that it exists finitely, but either f of c is not defined or limit x tends to c, f of x not equals to f of c. Okay. So what type of discontinuity? It's a removable one again. So f is the point, c is the point of removable discontinuity. So in this case, f is said to have removable discontinuity at c. Okay. Whether f of c is defined or not defined, we have a very simple example that you can take the same example. F of x is x square minus 4, but now take the point. So example is that f is now defined in between minus 1 to 1 to r. C is the point 0. It's an interior point of this interval, and you have fx equals to x square by x if x not equals to 0, 1 if x equals to 0. Okay. I mean, just we made in such a way. Now, actually, 0 is such a point that really, okay, like make take instead of 0, take something else. That will look better because it's look really bad. So let's say 1 by 2. Okay. So like then you have fx is x square minus 1 by 4 by x minus 1 by 4 half, and if x not equals to half, and 0 when x equals to half. Fine. So obviously limit x tends to half, fx will be 1, correct? What is the limit? Limit x tends to half, fx is nothing but limit x tends to half, x square minus 4 by x minus half, so it will be 1. So obviously not equals to f of c. So you can redefine it and so that you have removable discontinuity. So it's a very simple discontinuity. So we don't have to bother much about this. Okay. Okay. Now let's say, so another possibility is there in under removable discontinuity is that limit, okay, Okay, now second case, that limit x tends to c plus fx and limit x tends to c minus fx both exist, but they are unequal. Okay, both exist but are unequal. So if they are equal, then obviously that limit x tends to c fx exists. That we have the first case. Now both exist but they are unequal. So obviously f has a discontinuity at the point c, and we will say that both exist in the sense that both exist finitely. Okay, when we use the word exist, most cases, okay, I should mention that it exists finitely. Okay, so but they are unequal. So in this case, we will say that f has a jump discontinuity at the point. Okay, or this type of discontinuity is called the jump discontinuity of the function. Okay, so this type of discontinuity is called jump discontinuity. Yeah, we are about to end. I mean, what is the time? So 8, 10:30? No, what is the time? 20 minutes we have. Okay. Okay, so I have to go first then. This type of discontinuity, okay, I am just writing discontinuity. In this case, C will be called the point of the jump discontinuity, and we can define the total jump of the function. Okay, so let's define JF of C. That is the total jump of f at C. What it is? It is limit x tends to c plus fx minus limit x tends to c minus fx. Okay, what is the notation we'll use? We'll use that c plus 0 minus f of c minus 0. Okay, so this is the notation we're going to use. This is total jump of the function. Okay, okay, what is the example? Can you give an example of a function which has jump discontinuity? Yeah, we can take a step function which has jump discontinuity, or you can define any function. Okay, so fx like x plus 1 if x is greater than half, and x minus 1, x minus half if x is less than equals to half. What is the limit? X tends to half plus fx. It is limit x tends to half plus x plus 1, so we will have 3 by 2, and limit x tends to half minus fx is limit x tends to half minus x minus half, so it will be 0. So they are unequal, and therefore it has jump discontinuity. What is the total jump of this function? The jump of the function at half is 3 by 2 minus 0, so 3 by 2. Okay. Okay, so till now whatever we discussed, like for this when C is an interior point, removable and discontinuity and jump discontinuity, they are called the first kind of discontinuity or simple discontinuity. Okay, so removable and simple discontinuity will be called first kind of discontinuity. That means what? That means limit x tends to c plus fx and limit x tends to c minus fx both exist finitely. So then but we have a discontinuity. That type of discontinuity will be called first kind of discontinuity. Okay. So first kind of discontinuity means first type or simple discontinuity when we have if limit x tends to c plus fx and limit x tends to c minus fx both exist finitely. Okay. So now obviously next our idea is that let's say at least one of them does not exist. Okay, and let's see what we can do with it. Okay. So case 2, okay, I'll write down the later all the thing. So at least one of them does not exist. So at least one of limit x tends to c plus fx and what is going on? Does not exist. But f is bounded, let's say, but f is bounded in some deleted neighborhood of C. Okay. But f is bounded in some or on some deleted neighborhood in the C delta of C. Okay, in the interval obviously because it's an interior point and I'm not taking as an intersection. Okay. Okay, in this case, this type of discontinuity will be called oscillatory. Like we did in the last case, this type of discontinuity will be called oscillatory discontinuity. Okay, so this type of, so these are all second kind of discontinuity. Okay, this type of discontinuity is called oscillatory discontinuity of F. Okay, at C. So C will be called the point of oscillatory discontinuity. So that oscillatory just means finite oscillatory discontinuity. Okay. So since F is bounded, what will happen? That limb soup. So there are many other things we have to discuss. Okay, we have very less amount of time. Okay. So what? Okay, I'll just tell you. So since F is bounded on that on a neighborhood of C, what will happen? That upper limit, so limb soup x tends to C plus fx limit inf x tends to C plus fx limb soup x tends to C minus fx and limb inf x tends to C minus fx all will exist finitely. All will have finite values. What we're going to do? We'll take the maximum of all of this and then minimum of all of this. Okay. So let me define. So all of this exists finitely. Because it's a bounded in some neighborhood. So if we define mf of C as maximum of all this number, maximum of, okay, I am using short notation. What is the short notation? fc plus 0 bar means supremum. Then f of c plus 0 lower bar means infimum. Then f of c minus 0 upper bar means this supremum. And f of c minus 0 lower bar means infimum. So we can calculate the maximum value. These are finite number. So maximum value. And then we have small f of c is minimum of same numbers. This f of c minus 0 this, f of c minus 0 this. Then what we are going to do, we will calculate a new number which is mf of c minus small mf of c. This will be called the oscillation of the function at the point c. Okay. So this quantity will be called oscillation of f at c. So oscillation is also going to be a function, okay, for each value of. So you can see that what will happen if a function is continuous at a point c. The oscillation value will be, it will be 0, because all 4 will be equal for a continuous function. Okay. I mean, obviously it should be defined at the point c. If it is not defined, then obviously it will not be like that. At least in the first kind of discontinuity, at least removable discontinuity, we have this value will be equals to 0. Okay. So that's how we define the oscillation for an oscillatory discontinuity. In general, we define it for oscillatory discontinuity. Okay. So now what is the next case? So again, that it is unbounded in each neighborhood of C. Okay. So okay, we'll discuss the example in the tutorial because we don't have time right now. So let's say if be unbounded on every neighborhood of C. So that means what? At least one of those 4 will be infinite or will not be. So since f is unbounded on every neighborhood of C, on every actually deleted neighborhood, how should I write? Deleted neighborhood of C. So at least one of like C plus 0, f of C plus 0 minus f of C minus 0, C minus 0 this, at least one of these 4 will be infinity or minus infinity. Okay. So will be infinity or minus infinity. Okay. At least one of these 4 will be infinity or minus infinity. Okay. Leave them. Just pay attention over here. Okay. Okay. So in this case, we also have other cases. So if these two both are equal to infinity, or let's say both of them equals to minus infinity, then we have one particular type of discontinuity. But or let me write it down. So if each, okay, we have 10 minutes, each of f of C plus 0 and f of C plus 0 minus this is infinity or minus infinity, then f is said to have infinite discontinuity at the point C, right endpoint C. Similarly, so both have to be same value and either it is infinity or minus infinity. In this case, we will say that f has infinite discontinuity at the right endpoint of C. Similarly, if both C minus 0 and C minus 0, this is infinity or minus infinity. So both are equal now and both are infinity or both are minus infinity. in this case we will say again that f has infinite discontinuity at the left endpoint of C. Okay. Now what is next possibility? So this and these two values are unequal, this and these two values are unequal. Okay. So then we have infinite oscillatory discontinuity. Okay. So ultimately, let me write down a whole picture because we have very less time. Okay, so I will continue a little longer. Okay. So now the case is that limit c plus 0 is not equals to f of c plus 0. So limit infimum and supremum are unequal in this case. So in this case we will say that f has infinite oscillatory discontinuity at the right endpoint of C. Okay. Or right of C, not end, basically right of C. Okay. So in this case, f is said to be infinite oscillatory discontinuity at right of C. So in the word in is not good because C is an interior point. So just right of C. Similarly, if f of C minus 0 not equals to f of C minus 0, then what we'll say? It has infinite oscillatory discontinuity at left of C. Okay. So in all cases, what we're going to do, we'll calculate again MF of C, which is maximum of f of C plus 0, f of C plus 0 bar f of C minus 0, f of C minus 0 this. And also we'll calculate small m of C, which is minimum of f of C plus 0, f of C plus 0 is f of C minus 0, f of C minus 0. Now in this case, it might possible that m of C will be infinity. Okay, or this might be infinity and minus infinity, now it's allowed. In the last cases, that was all mf of C and small m of C are finite value. Okay. Now if it is okay to define, then we'll define again the oscillation of f at the point T. So this is again oscillation. You can see that if it has only infinite discontinuity but not infinite oscillatory discontinuity, then these values, I mean, either it's infinity will have or minus infinity will have. Okay, so like minimum and infimum will be same in that case. Okay, you'll get the oscillation will be zero in that sense. Okay. Okay, so let me now write down the whole picture. So now we already have a picture for left endpoint. So now C is an interior point of C. So F has as a discontinuity at C, where C is an interior point of I. Okay. Now again you have different possibility. First possibility is that limit x tends to C fx exists. What type of discontinuity we have? Then we have removable discontinuity. Fine. So now second case is does not exist. Second case is limit x tends to C plus fx not equals to limit x tends to C minus Fx. So under this case, if there exists a neighborhood where f is bounded, so if f is bounded in some deleted neighborhood, what type of discontinuity we have? We have oscillatory discontinuity. Okay, I forgot that. Uh, but both exist finitely. Okay, I forget that part. They are not equal, but limit x tends to C plus Fx and limit x tends to C minus Fx exist finitely. Then we have jump discontinuity, correct? In this case, you will have jump discontinuity. Both exist. This limit and this are exist, but they are unequal finitely. Then you have jump discontinuity. And then we have, let's say, one of them does not exist. At least one of them does not exist. No, removable is when limit exists. Limit exists, then you have removable. But here limit does not exist because right hand limit and left hand limit are unequal. So therefore limit does not exist. So that means you cannot remove that discontinuity. And what we have jump. So this exists finitely means you can calculate the jump. Okay. And the next thing is that they does not exist finitely. Okay, at least one of them. So at least one of limit x tends to C plus Fx and limit x tends to C minus Fx does not exist finitely. So under this case, you have like f is bounded on, so all this type of discontinuity is first kind. Okay. Now what we are discussing is second kind of discontinuity. So f is bounded on some deleted delta neighborhood of C. So in that case, because it's a bounded, lim scope of C plus, lim imp of C plus, and similarly C minus all exist finitely, and we have what? Oscillatory discontinuity. Okay, and we can calculate the oscillation, and oscillation will give you the finite value. Okay, and now in this case, that f is unbounded on each delta neighborhood. F is unbounded on each deleted delta neighborhood. Actually, delta neighborhood is fine of C. Okay. So now under this, if lim sup of C plus and lim imp of C plus exist, so like if f of C plus 0 is same as f of C minus 0, let's say infinity or minus infinity, then it has infinite discontinuity at right of C. So infinite discontinuity. right of C. Okay. And similarly, for f of C minus 0, f of C minus 0, both are equal, and either it is equals to infinity or minus infinity, then we have infinite discontinuity at the left of C. And what is the other case? They are unequal. Okay. There is one more. Oh, sorry. Yeah, thank you. C plus 0 is infinity or minus. So other thing is that they are unequal. Then we have oscillation. C plus 0, let's say C, they are unequal, say then you have the infinite oscillatory discontinuity at the right of C. Similarly, if f of C plus 0, so infinite oscillatory discontinuity at right of C. Similarly, you have the infinite oscillatory discontinuity at left of C. So these all this type of discontinuity are second kind. Second kind of discontinuity. Okay. Okay, we'll see examples in the tutorials. We'll solve some examples. But the meantime, I was thinking about to prove some theorem, but will not get the time. Just let me inform you. So if we have a function f which satisfy intermediate value property, then it cannot have any discontinuity of first kind. So if that function has a discontinuity at a point, then it should be a discontinuity of second kind. Okay, if we have a function which satisfy intermediate value property. Second, if we have a monotone function like monotonically increasing function or monotonically decreasing function, if it function has a discontinuity, it's always a first kind discontinuity. It cannot have discontinuity of second kind. Okay. So like we know that derivative of a function satisfy intermediate value property. So that means derivative of a function cannot have discontinuity of first kind. Okay, by Darboux theorem, I think you are familiar with. Also for monotone function, the set of all possible discontinuity is at most countable. Infinite, it cannot be an uncountable many points where monotone function are discontinuous. Okay. Okay, so there are many other things, but we will not get the time to discuss. But let's see what we can solve in the tutorial. Okay, so that's all from my side. So any question from online participant? Is there? No one. Any question from online participant? No, I think we should stop. Okay, then we'll start the next session after 15 minutes. Okay.
We will start the session now. Yeah. Yes. Can you hear? Huh? You would have the meeting. Yeah, you are left the meeting. Connect to this. Hmm? Okay. If any hand drops here, tell me. I'll come back. So we'll continue discussing group actions, which I introduced yesterday during the tutorial session. Yeah. So we have defined what it means for a group to act on a set. Okay. That means that there is a multiplication involving one element from the group and one element from the set, which results in an element set. So you think of x as a set of points, and then think of x as a set of points, and g is acting on x. So every group element acts on a point in the set to give you another point in the set. Okay. The properties are that the identity element of the group must fix every point of the set, and that the action is compatible with the multiplication in the group, in the sense that if you take g dot h dot x, gh dot x. Okay, then we've defined orbits and stabilizers and looked at the orbit stabilizer, proved the orbit stabilizer lemma, very quick proof of orbit stabilizer lemma, which says that the order of the group is equal to the length of the orbit times the order of the stabilizer for any point x. So orbit and stabilizer are defined for a point, not for the entire action, for any point in the set. Okay, so whatever x you take, you get an orbit of x and stabilizer of x. So if you take order of e is always equal to or length of orbit of x, that is size of the set orb x, multiplied by order of the stabilizer. Order of the stabilizer because stabilizer is a subgroup. When will the stabilizer be a normal subgroup? Just a side remark. When will the stabilizer be a normal subgroup? If the orbit is of size 2. Why? Any subgroup of index 2 is normal. Okay, index you are not defined, but you know it. Index of a subgroup is one way to see it is order divided by order of subgroup. So you have not total Lagrange theorem, which says that order of the group divides order. But anyway, the index is the number of left cosets or number of right cosets of the subgroup in G, which is constant, and that is equal to order of G divided by order of the subgroup. Okay, so that's one thing. But more generally, so why does it happen here? Because the index. This is another way of saying that the index of the stabilizer subgroup of any point x is equal to order of G is equal to length of the orbit, right? Equal to length of the orbit, because so this notation for index this will be equal to length of the orbit. Yeah, so you're right. If the length of the orbit is 2, that's one case where the stabilizer has to be normal. But more generally, when is it normal? A necessary and sufficient condition. This is a sufficient condition, but it's not necessary. Necessary and sufficient condition can be anything other than the trivial statement that it's normal, because there's no answer for a condition, right? So many different conditions may characterize something. So if you think about this in terms of this, can you say anything? Yes. Gx equal to stabilizer of Gx equal to stabilizer of x for all g. That means if all the elements in the orbit of x have the same stabilizer, all the elements in the orbit of x have the same stabilizer, then that stabilizer is normal. Right. So this is g times stabilizer of x, g inverse, right? Conjugate of stabilizer. So we want this to be equal to tab x itself. G, for all g, g stab x g inverse should be equal to stab x. For all g, stab of g dot x should be equal to stab of x. But all g dot x means all the elements. What are g dot x? All the elements in the orbit of x. Orbit of x is this, right? Orbit of x is set of all g dot x for g varying over g. Correct, for the fixed x. So for every g dot x, we want tab of g dot x equal to tab of x, which means all the elements in the orbit of x have the same stabilizer. In that case, the stabilizer of x will be a normal subgroup. Okay, and vice versa. If it is normal, then again, because of the equality, it has to work out this way. Okay, so the stabilizer will be normal if and only if all elements in the orbit of x have the same stabilizer, have that stabilizer. Okay, this is just a character. It doesn't give you much else, but sometimes it is useful to know that. But definitely a special case of that is, so in fact you can say that if the orbit of x has size 2, length 2, then both the elements in the orbit have the same stabilizer, because then you can infer that it is normal. And then using this condition, you can say that okay, both elements must have the same stabilizer. Okay, yeah. So we'll continue. Okay. So how do you Lagrange theorem normally? You say that you define cosets either explicitly as set of so coset if H is a subgroup of G, then you define the coset as set of X belonging to G as a left coset, and then you, or alternatively you can define an equivalence relation on G by saying X is related to Y if and only if X X inverse Y is in H. Okay, or X in H also works. Yeah, same. X that will give you the right coset characterization. Anyway, if you take this, then you'll get when they are in the same left coset of H. Okay, so you can define this relation, and then the equivalence of X will be this equivalence relation. The equivalence class of X will be left coset, and you can show that it is the usual definition of left coset. Okay, so that you get a partition, and then you show that all the different left cosets have the same number of elements. Each any two left cosets the same number. Then partition the group. So you take the sum and so on. Okay. So, but if you've already done this orbit stabilizer lemma, you can just use it to prove Lagrange theorem. So let's just look at that. Okay. So Lagrange theorem using Lagrange theorem using orbit stabilizer. So to use orbit stabilizer, you need some action of a group on another. What do you define here? Do you define action of G on H? That won't work. Okay, because if you multiply, say, group element with subgroup element, some arbitrary group element, if you multiply with subgroup element, it may not stay inside the subgroup. That won't be an action. Otherwise, you take some action like conjugation. Conjugation is also action. Even that will be an action only if it is normal. Otherwise, it won't stay inside the subgroup, right? So you can't do that. So instead, you define action of H on G, but by left multiplication. Okay. So H dot let's say X equal to X. Sorry, the usual group multiplication Hx for all X in G. This is well defined. Correct. It's well defined. Whether it's an action or not, we'll see, but it's definitely well defined because you cannot go outside the group. Group is closed under the operation, its own operation. So you can't go outside the group. So it's well defined. No, is group action 1 dot X is 1X, this is of course X. And if you take H1 dot H2 dot X, again, this is simply, I'll just write in one step. It is just H1 H2X, which is of course H1 H2 dot X. So yes, it is a group action. Okay. It is a group action. Then what does orbit stabilizer lemma tell us? Order of X is equal to for any X. Okay. What is stabilizer of X under this? We want H dot X to be equal to X. If H is in the stabilizer, stabilizer consists of what elements? Group elements or points? When you think of this as a set only. Okay. Just think of this as a set, not a group. Yeah. So stabilizer consists of group elements, that is H elements. So this must be a subgroup of H. So when will this is the definition simply. That means Hx equal to X. When will that happen? H is identity. So that means the stabilizer is trivial. Okay. So order of H is equal to cardinality of orbit of X under this action. Correct. That is cardinality of what is orbit of X? That is an X plus. It is just Hx. Because orbit is in general D is acting on an X, then orbit is all the elements of the form G dot X. Here H is acting on X equal to G. Okay. So it is all the elements of the form H dot X. For fixed X, varying H varying over capital H. Right. So orbit of X okay. So that is of course Hx. So this tells you that every right coset, now you can define right coset, every right coset has the same order. Fine. And then you know that G is partitioned into this, and then the remaining argument is as follows. Rest of the argument is same as the usual proof of Lagrange theorem. But from this, you immediately get that every right coset has the same number of elements. Okay. Every right coset has the same number of elements. Or yeah, you can first start by observing that because the orbits partition G. Yeah, in fact, you can just say that if you take G is a finite group, assume. So you can do it for infinite group also. So G is a finite group. So if you take the distinct x1, x2, etc., xk are distinct representatives of. I think I'm forgetting right large enough. X1, etc., xk are distinct representatives of the orbits, unique representatives of orbits. Then G must be equal to the union because it's partition to the, and because it's a partition, you can just write this is summation I equals 1 orbiter xi. But then according to this, that is equal to summation I equals 1 to k order of h. So as usual, that part not really different. The only thing is if you already did group action, then you can get this immediately. You don't have to again define coset and again prove things because cosets are exactly the orbits of the action. Okay, that's all. Yes. Is it? You can't hear? What do you? Let's check once. Can you hear? Huh? No. No, you can hear. Please step on. No, you can't hear. There is a lag, is it? Oh, again, there is problem with port, I think. No, it's fine. Okay. Yeah, sorry about the audio. Okay, we'll continue. Fine. So, what are the usual corollaries of Lagrange theorem? One is that the order of an element of the group divides the order of the group because the order of an element is exactly the order of the subgroup generated by that element. Again, I will not discuss subgroup generated by element, but very briefly, if you take a set, subset S of G, then we say the subgroup generated by S is the smallest subgroup, subgroup generated by S, the smallest subgroup containing S. Small sense that if H is any subgroup for which S is a subset, right, it is containing S, then uh, then this is contained in H. Okay, so this is, and this is a subgroup. So one way to define it is this is a subgroup of G, and if H is any group G containing H is any subgroup of G containing S, then subgroup generated by S is also contained in H. Okay, another way is you can define it a little more explicitly as intersection of all subgroups, intersection of all subgroups of G containing S. Okay, this is little more constructive than this, right? But still not very constructive. So the most constructive definition is what? Can you explicitly say what this will be? Huh. Okay, so you take Yeah, you take the set of all elements of G of the form x1, x2, etc., xk, where xi belongs to S union S inverse. Maybe I should actually better notation is, yeah, S inverse like this. S union S bracket inverse for I equals 1 to k. K is any non-negative integer. Okay, so when it's an empty, when k is 0, what is the definition of this? Empty product is defined as identity element. Like power 0 is defined as identity element. Empty product is defined as identity element. Okay, with the definition in place, you should take all the products of this form. Otherwise, also you can get identity because you can get x1 inverse, for example. Right? Anyway, S inverse is a notation for elements x inverse for x belonging to S. So you take in another way of saying that is you're taking elements of the form x1 tilde, x2 tilde, etc., xk tilde, where x1 tilde is either x or x inverse for x belonging to S. Okay, like that. This is just a different way of saying the same thing. Or more generally, you can write powers here, epsilon 1, epsilon 2, and say they are all plus or minus 1. Anyway, different ways of writing. So this will be an explicit definition of the subgroup, and you can prove that these are the same. These three definitions are the same. So these are really three definitions. This is another one. It's more or less obviously the same as this. Okay, the first and second definitions are more or less obviously the same, but you can prove that the third one is also equivalent to the other two. Okay, so in the special case where you take uh, S as a singleton set. Okay, so if S is a singleton set X, then you write S as just, then you write subgroup generated X as just angular bracket X. And this is what is called the cyclic subgroup generated by X. Okay, and so we know that the order of sub excuse me, order of subgroup generated by X is equal to order of X. What is the definition of order of X? Least positive integer k such that is to get is identity element of G. Okay, so that's a different definition, right? You're not defining order as number of elements. It's just least positive integer k such that x or k is equal to 1, but that happens to be equal to this. Okay, and then the basic and then G itself is said to be cyclic group if G is equal to cyclic subgroup generated by X for some X in G, and then you say that X is a generator of G. Okay, so what is the basic property of cyclic subgroup? Cyclic group or subgroups of cyclic group. What can you say about them? They are also cyclic. So in this case, H is also cyclic. Okay. Any subgroup of a cyclic group is cyclic. And what about quotients? Quotients of cyclic groups also, right? G mod H is also cyclic. So I have to say H is normal subgroup. Cyclic group is abelian. So every subgroup is normal. So every quotient is every cyclic group is cyclic. Okay. There is something called metacyclic group. Is if it has a normal subgroup such that such that both n and the quotient of g with respect to n are cyclic. Any examples of this? Any cyclic group is definitely an example, because you can just take n equal to g or n equal to 1. It's trivial subgroup, either way. Right? So trivially cyclic groups are all metacyclic. Okay. Any other non-cyclic example? Abelian non-cyclic example? Klein 4 group you take, then you take any non-trivial proper subgroup. Quotient has to be, that is cyclic. And why is it? I mean, you can see that it is, but can you argue in a more abstract manner why that must be true? If I give you that it has non-trivial proper subgroups, if I tell you that Klein 4 group definitely has some non-trivial proper subgroup, then without looking at what they are, can you tell me why it must be metacyclic? Klein, okay. Firstly, Klein 4 group is what? Smallest non-cyclic group. Okay. Second thing is it is abelian. And I tell you that it has at least one proper non-trivial subgroup. Then it must be metacyclic. Why? Order 2, yes, but don't say order. I'm not telling you the order. Yeah, without mentioning the order. So you take any, yeah. No, even you don't know the order. I'm not telling you the order. I'm just telling you the smallest non-cyclic group. Suppose you don't know what it is. It has, so I'm telling you G is the smallest non-cyclic group, and it has some. I'm not even mentioning abelian or not. It has some proper subgroup. N. Okay. So yes, this is it. Then G must be metacyclic. Why not? Suppose it. What is order of G by N? In this case, yes, but it is less than G. Okay, it's less than G. What is the order of N? Also less than G. But G is smallest. I just want to do that. Examples of metacyclic group. Okay, any subgroup of the normal subgroup of the there will be the group of million and then what C plus okay. This you mean YouTuber? No, you use this one. Uh, yeah, now it is. I think now it should be fine. What is this called? What is this thing called? 255. Lucas. 255. Right? Okay. Can you hear now? Fine. Hopefully it should be fine now. Sorry. Huh? Is it? Okay. I think now it's okay. Now that plan is working. No, it is starting. Fine. Okay, I'll continue. Fine. All right. So that's fine. Using the idea group actions, we'll just briefly discuss P groups. So the general definition of a P group is G is a P group where P is a prime if every element of G has order P. No, order P to the power K for some prime power order, not K is not fixed in advance. Each element has some P power K order. That's afterwards. Okay. Every element has order a power of P. That's it. Not necessarily the same power. Obviously, that's not possible. Also, at each identity element will have only order one. Right? So each element has order some prime power, particularly power P, not different. P is fixed in advance. Okay. P is fixed in advance. In the finite case, this is equivalent to saying G is and G is a P group if and only if G is P power n. Okay. Or some n, let's say trivial group is also P group. If only G is order some prime power, that is the finite case. Infinite case, of course, that doesn't make any sense. Is there an infinite group? Can you think of an infinite group where every element has not a finite order, a power of one fixed prime P? ZP. Okay. element wise study. Okay, so I get it. In fact, I'll define this. So you take set of all sequences from with terms in ZB, correct? From N to ZB, but not all of them. Okay, I know what you mean. So fine, you can take all of them. In that case, what is the order of every element? Any non-zero element will have order P. Okay, yeah, so that is one case. Any non-zero element here will have order P. So this is a finite P group. Okay, correct. Good example. This is a particular group with finite exponent. Okay. It's an infinite group with exponent is what? So with this property. That is, any group G is said to have exponent n. If x power n is equal to e for all x in G, then it is the smallest positive integer having this property. I'm not writing the elaborate definition. Smallest or least positive integer with this property. Okay, that's not the same as order of x because x is varying over all G. For example, exponent of S3 is what? What is the exponent of S3? 6. Some elements of S3 are order 2, some elements are order 3, and of course, identity element is order 1. So, if you want one power such that anything in S3 raised to the power is equal to 1, that is 6. The smallest such is 6. Other one is 12, and so on. So, any higher one works. So, it's like when we define period also, this is the fundamental period, like that. Okay. So, any group with yes, smallest. So, order of the group is all. If you have a finite group, then order of the group is only one such n. It may not be the exponent. So in Klein four group, what is the exponent? 2. Okay. Generally in Z2 power n, or if you take ZP power n, ZP power some finite n, or Z whatever Zn power m. Okay. Then Zn power m will have exponent n. Because Zn has exponent m. So when you take power m, that is direct product, that will be the same. But an infinite group also can have a finite exponent, as this demonstrates. Now I want an example of infinite group without an exponent. Exponent is infinity, you can say. Okay, that means an exponent, but it is P group. So modified example. In this case, every element order at most P here. One where elements of order P exist, P square, also P cube, also P power 4, and so on. All of them. Okay, another question is, do you know any infinite group, P groups, any infinite group in which all elements are finite order, but there is no exponent? All possible orders occur. Huh? All the components that power in this one. So consider all Z in C such that z power n is equal to 1 for some n. Sorry, for some n in n, not n 0. For some positive integer n. Okay. Then is this a group under multiplication? If you multiply any two, then definitely what will be the, so suppose that is what element means, z1 power m is equal to 1, z element power m is equal to 1. So if you take z1 and 2, what do you have to take? Power LCM of m. You can take mn easily. You can take LCM of mn. Okay. So power then will be 1. So yes, it is closed under multiplication, and then inverse, of course, to z power n is 1, z power minus n is 1. So z inverse power n is 1. Inverse are there. Identity element 1 always satisfies. So definitely this is a group. It's an infinite group. Yes, because you can take, if you take a fixed n, then you get only n values, right? Or a particular line, if I take 3, any cube roots of unity, complex cube roots of unity are there? Only 3. Sorry? Voice is again not clear. Okay, yeah, no option there. Hopefully the recording is fine, so I'll upload it later. Okay, so so these are all complex n roots of unity for all n, not for fixed n. If you take fixed n, you get finitely many. So in fact, finitely many elements of a given order. That is true. Of a given order, finitely many elements will be there. But all possible orders. So there is no exponent. So there is an infinite periodic group. Group is periodic or also called torsion. Torsion is applied more in the case of abelian groups, but even here you can apply. So infinite torsion group means, torsion or periodic group means every element has finite order. So this is just that with no exponent or with infinite exponent. Either way you can see it. Exponent is like something like a characteristic of a ring. Okay, not the same thing. Right, is it? Yeah, characteristic of a ring is the exponent of the additive group. Correct. Characteristic of a ring is the exponent of the additive. It already knows one. Yeah. Fine. So this is an infinite group with periodic group with no exponent. If you modify this very lightly, an example of infinite P group with no exponent. Here you will get all possible orders. I don't want to which are powers of a particular. So only thing you have to do is, yeah, replace n by p power n. Okay. So you have an infinite P group with no exponent. Again, the question is it a group? Yeah, then I mean, again, you don't have to do that hard work. You can just say to the power p power m plus n. That will work. But if you want smallest one, then p power max of m comma n. That will also work. Okay, instead of taking LCM. I mean, that is the LCM, correct? The same thing. So this also group inverses, everything will be there. This is an infinite p group, and this is called the proof for p group. Okay. proof of P group for that particular yes. For Z power n. Yeah. So if you take Z power n equal to 1. So by definition, if you have any element Z, then for that Z power n equal to 1 for some constant integer n. So its order must be finite. Or else what are you thinking? Period. Okay. In a group, periodic means every element has finite order. That's it. Periodic group means every element has finite order. Group may be finite or infinite. So group order may be finite or infinite, but every element has finite order. That is the meaning of periodic group. So it is not repetition in that function periodicity is not the same thing. But of course, there is in that way, if you want to see, if you want to relate periodicity of that to this periodicity, then what you say is if you take Z. So this repeat. In that sense, it is periodic. But for each element separately, there is no way to define it for all elements at the same time. Yeah, for each element. So each element has finite order, but one that is what it has no exponent. So there is one which makes all the elements equal to one when you take the power. There is no one such. That is why exponent is not defined. Right? Exponent of a group means what? One n means for all the elements of the group. When you take to that power, it becomes one. It becomes identity. That is not there in this case. That's why we have to define it in such a slightly complicated way. Let's say, okay. If you want just infinite group with uh, what is it, infinite periodic group with possibly finite exponent, then the earlier example is fine. This one. Or in fact, in general, you can take Zn power, lf naught, right? Or anything, any infinite. So there are so many Zns if you take for the same end. All of the elements have order at most 10. At most 10, some of smaller orders. So this is definitely periodic, but it has exponent n. This is the exponent n. So we want to stress the definition, right? Stress is the definition basically and check what all different possibilities are there. So I want infinite periodic but no finite exponent. Is that possible? Yes, even that is possible. So that is a variety group theory that you have all these different possibilities. Okay, so this is called true for P group. There are other ways of defining this. One is called the direct limit. So the limit construction I will not do. It's an interesting construction to do, but very attractive. So in limit construction, basically if you have dealt with proofs using Zorn's lemma, where you prove the existence of something, some kind of maximal thing, by taking a chain and then taking the unit. It is something like that. What you're taking, the different objects you're not taking are not literally subgroups or sub objects of one thing. So they're not subsets of one thing. Instead, you connect them using, instead of inclusion relation, subset relation, you connect them using homomorphism. In fact, it can be more general than this. So you can also have some. So you have some kind of thing called a directed system. Okay. So these are all different groups where there are homomorphisms from each element to some next element. So it's a generalization of a sequence, except that generalization of a sequence in the sense instead of just this online people cannot. So instead of just this part where it's just something, you have more of a poset kind of structure where it's a directed system where there are other things also which are maybe like G1 and G4, there's no relation between them. So they are not comparable in that sense. However, both of them go into some common thing. Okay. So if you take any two, G1 and G4, for example, they both have homomorphisms into one common group. Say, yes, there are some detailed definition. So this will form what is called a directed system. Then for this directed system, you will define okay limit of the system, and that will be some G. Okay. So I'll just use this notation. Okay. So limiters you will define as G in a particular way such that there are homomorphisms from all of these into this. Okay. And G is minimal in some sense. So this will be what is called a direct limit. The proof of P group, this you can at least intuitively understand. You take ZP. Okay, by the way, we not start this way. You can have it infinitely descends downwards, that is possible. So there are so many here. Okay. So you take ZP. If you take ZP square, is there an injection from ZP to ZP square? Is ZP a subgroup of ZP square? Not with the same labels, but with the different labels. For example, if you take Z, let's say Z27, can you get Z9 in this or Z3 in this? What are the elements of Z27? 0, 1, up to 26. You take element 9 and generate subgroup. What is its order? 3. So that means you can realize Z3 as a subgroup of Z27. Okay. But in between, what is also there? Z9. So in fact, you can realize Z3 as a subgroup of Z9, Z9 as a subgroup of Z27 in such a way that these morphisms, so if I call this I1 and I2 as inclusions, as a sort of inclusions, embeddings, then I2 composition I1 is an embedding of Z3 into Z2. So it's not just this, you have one embedding here, okay, of Z3 into Z27 such that it's a composition of P. So you have this infinite chain. In this case, it just starts with ZP. So you have this infinite chain, okay, of P groups, particular finite P groups, cyclic P groups, in fact. What is at the end? This does not end. This goes on forever. But I want one group into which all of this embeds. Okay. I want one group into which all of this will embed. In some sense, it's minimal. So that is exactly our proof of P group, which we in fact write as ZP infinity. Okay. It's like you're taking the infinite power of P, which doesn't actually make sense, but is just the notation. Okay. So this is not part of this chain, it is outside the chain, but again, all of these will embed into it. So if you see that previous definition, it's the same thing, right? You can find any ZP or EP, let's say, or CP power n, subgroup of this, correct? If I write this as CP power infinity, every particular P power nth roots of unity, that group, that is a subgroup of this, because if you take the P power n and take only those Z, that will be a subgroup of this. So all of these embed into it, right? So in an additive notation, you write it as ZP power infinity and ZP and so on. So this is what is called direct limit. We won't formally define this, but just to give you an idea. So there are more examples of more non-trivial examples of direct limit. So this is an interesting concept. Okay, fine. Let's go back to finite groups. Sorry, finite P groups. Now let G be a finite P group. Consider the action of G on itself. I actually start with just a finite group. then come to finite P group. Consider the action of G on itself by conjugation. So is that an action? Easily verify that it's an action. Then what is orbit of an element under this action? G dot x means Gx G inverse or G x. Right. So this is the conjugacy class. This is called the conjugacy class of the element x. That is, any element of the form Gx G inverse is called a conjugate of x by the G. I think we find it before also. So the conjugacy class of x is a set of all conjugates of x. What is the stabilizer of x? That is set of all elements of G such that Gx G inverse is equal to x itself. G dot x should be x itself. That means Gx G inverse equal to x itself. This is what we call the centralizer of x in G. Okay. Now again, we know that the group, this one, both are G. This group is partitioned into its orbit, right? So G is union of conjugacy classes. In fact, those are usually denoted as small c effects. Okay. X unique represent. In fact, I'll start from x0 okay. or x1 representatives of conjugacy classes of all the conjugacy classes. Okay. G can be written as union of conjugacy classes. So order of G is equal to summation understand that I'm not taking union over X in G, only one element from each conjugacy class, right? Otherwise, this is going to be counting. Okay, so I don't want to do that. Take only unique representatives from every conjugacy class and some more that. But this is also equal to, according to orbit stabilizer lemma, order of orbit, length of orbit is order of G divided by order of stabilizer. That means index of stabilizer in G. Stabilizer being the centralizer here. Okay. So centralization. So order of index of the stabilizer. Now when will the orbit be singleton? When will the orbit of an element X be a singleton set? It's a non-empty set always, correct? Because X itself has to be there. When will it be a singleton set? Yes. If X commutes G for all G, if X commutes all the elements, that means X is in the center. So if X is in the center, these terms here also you can see, here also you can see. If X is in the center, first of all, CG of Xi is D itself. Right, centralizer is the entire group. That's why it is in the center. Okay, so from here, otherwise, directly from here, the conjugacy class is singleton. Just directly reason out Gx G inverse equal to X implies Gx equal to Xg. So if it happens for all G, X commutes with everything. So in that case, you'll get so many terms which are one. Okay. because the length of the orbit is 1, right? How many will be there? Number of elements of center. So order of center. Plus the remaining. So only those with non-singleton conjugate classes, or another way to say that is CG of xi should be proper subgroup. CG of xi is a proper subgroup because CG of xi equal to G means singleton, right? So another way to say is CG of xi is proper subgroup. Okay. So I'll summarize this in the next thing. So order of G is equal to order of center plus I will now write J equals 1 to R and Y1 YR are unique representatives of all non-singleton conjugacy classes of elements of G. Okay, you take only the non-singleton conjugacy classes, take only their representatives, then you can partition that sum into this, which actually is not any single conjugacy class, but the sum of the lengths of all the singleton conjugacy, which is number of singleton conjugacy classes. That is order of Z of G. Okay, so this is, as you know, called the for any group. Now, if you take in particular, G is a finite P group. Then what can you say? So P divides order of G. Right. Is the finite P group. We know that finite is equal to saying it has order P. Okay. So P divides order of G. What about these terms? The second term, the summation. Sorry. The if you take conjugacy class of y, which is actually or the order consists of y. So order of G is some P power n, and order of T of yi will be some P power k. Okay, I'll write P power n, where m is less than n. Why? Otherwise, it is a proper subgroup, right? We have specifically taken those where it's a proper subgroup because otherwise this will be singleton. We know this is not equal to 1. This is not equal to 1. That means this is not equal to G, right? So this proper subgroup of G. Okay. The proper subgroup of G has order P power. So by Lagrange theorem, this order must divide G, order of G. So it must be some P power. Okay, fine. That means P divides this index, correct? Because it is P power n by P power n minus m. Does it follow, or do you want me to repeat anything here? Do you follow? So P divides this. So what do we have in this? P divides LS, okay, and also P divides this summation because each term in the summation it divides. So it divides the summation. So therefore, P divides this term, which means Z of G is a non-trivial subgroup. So any finite P group has a non-trivial center. Okay. Any finite P group has a non-trivial center. Fine. In particular, if the group is abelian, then the center is the entire group. But it may be non-abelian with a right. It will have non-trivial center though. Center is abelian. Right. Center is definitely abelian because set of all and commute everything. So it will also commute inside itself. Center is an abelian group. Then what happens is if G is a finite P group, then Z of G is a non-trivial subgroup of G. So then when you take G mod Z of G, this is again a P group. G modulo, you can quotient. So that is again a P group. So again that applies, this thing applies to that also. So right. So this will again have a non-trivial center, possibly equal to the whole group. Maybe it's abelian, right? So and so on. So you can keep doing this until ultimately what happens? Ultimately it becomes abelian because it's finite. So ultimately you must get one at some point when you divide. So the point before which you get one, that means before which this one is the quotient becomes trivial at some point because it's only finite. Each time you quotient, order becomes smaller, right? So at some point, this must become one. So you will start with G and so on. Okay, keep quotienting by the center of that group which you get repeatedly until you get the trivial group. So the point is ultimately you will get trivial group if you keep doing this. In general, okay. In general, suppose G is any group. Then you define say G naught equal to G, G1 equal to G naught mod Z of G naught, G2 is equal to G1 mod Z of G1 and so on. You define a sequence of groups like this. Sequence not in the sense of exact list of groups like this. Okay. So suppose this list. So I'm starting with some group, whether P group finite without any assumption. Take any group and keep doing this. Okay. So it is possible that Z of is trivial also. For example, can you tell me a group with trivial center? S3 has trivial center. So if you start with S3, then G1 will be equal to S3 itself. G2 will be equal to S3 itself. So you get, this is just a sequence in the usual notion of sequence, just a sequence, an infinite sequence, possibly the same. Or possibly after some time, all terms become the same because you get trivial center. That might happen. But if ultimately what happens in this is, if the sequence is eventually trivial, since at some point you get trivial sequence, you keep doing this after this. In the definition, you just keep doing this. But ultimately, if you get G naught, G1, etc., some Gn is equal to 1 after finitely many terms, some Gn equal to 1, after which everything else will be 1. Okay. Then this is called a nilpotent group. Then you say that is a nilpotent group. Okay. So the importance of this is that you can prove, for example, that finite nilpotent group is a direct product of P groups. Okay. So in fact, you can ask, will anything other than a P group satisfy this? Yes. Other than P groups, S3, for example, is not nilpotent because it has non-trivial center. That's one very simple case. If it has trivial center, then the sequence will never basically converge to one, so to speak, not the usual sense of convergence. It will never settle down to one because you keep getting the same group over and over, right? So there are, of course, groups which don't satisfy this property. So this definition makes sense. There are some groups which are not nilpotent, but of course, any finite P group is nilpotent. Correct. Then you can ask, are there groups other than finite P groups which are nilpotent? So definitely because it's a generalization of another, or it's a weakening of another property. Yeah, any abelian group. What is the center? Entire group. So in one step you get trivial, right? You take any abelian group A, any mod set of A is one only. So the sequence immediately terminates. Okay. So every abelian group is nilpotent. But can a non-abelian group be nilpotent? Yes. You can take a non-abelian P group. For example, Q8 again. Q8 quadrature of Q8 is a Klein 4 group. Klein 4 group is abelian. So as soon as you get abelian group, you can stop because in the next step you get one. Right. So if you start with Q8, you get Q8, V4, and then 1. Okay. So this is Q8 is a nilpotent non-abelian group because it's a P group. But if you take, for example, Q8 direct product with say, or even direct product with D4. D4 is also nilpotent because it's a P group as well. Or even you can, okay, you don't even need to do that because that's still a P group, so not a good example. Q8 direct product with, let's say, fine, just Z9 or any abelian group also you can take. So that will be a non-P group. So the idea is you are slightly weakening the condition of abelianness, commutativity. Okay, why is it a weakening of commutativity? One sense is that all abelian groups satisfy this property, but also the idea is that although the center may not be the entire group, when you quotient it, you get ultimately you get something abelian. So by quotienting, you can reach an abelian group. Not only that, you're quotienting not by something else, but by the center itself. So the center element commute with everything, and in the quotient, again, so whatever does not commute, that is what you get after quotienting in some sense. So you are reaching towards abelian group by only quotienting by the commuting elements. Otherwise, what is the, I think to stop now? Yeah, I'll stop in 1 minute. So what is the derived subgroup or commutator subgroup of a group? So you define commutator of a group, sorry, to commutator of two elements as or two, just two conventions. Are there any one you can take? One may be the inverse of the correct. Yeah. No, no, not inverse of the other. It will be different, of course. So this you can take as the subgroup of G generated by all the commutators, where a commutator is defined this way. So you take all the commutators, generate a subgroup using them. They won't automatically form a subgroup. Okay. Um, but actually, if you check for small orders, they will always automatically form subgroup. For small order, up to some order, I don't remember, 100 and something maybe. They definitely form subgroup without having to generate all the commutators if you take. But in general, they don't. So you take all the commutators and generate the subgroup using them. We have defined generated subgroup earlier. Okay, that is called the derived subgroup or commutator subgroup. Okay. So derived or commutator subgroup. Derived because if then oh, if you fix an element G, then mapping X maps to called a derivation. Okay? It's called a derivation on G. It's called derivation because it's something like the product pool of different. Okay, so it's called a derivation on G. Anyway, this is called the derived or commutator subgroup. So you can actually prove that this is always abelian. Because intuitively, what are you doing? You're taking x inverse, x inverse, y inverse. What does that? If you think of it as a quantity, what does it measure? X, y, x inverse, y inverse. What does it measure? Huh? So, okay, when will it be 1? If x and y commute. So it measures the amount of non-commutativity of that particular xy. Okay. So here you're taking whatever is preventing commutativity and then quotienting by that. Quotienting, when you think of quotienting, you should always think of cancelling out things. Okay. Or you're getting rid of things that you don't want, but not be subtracting. If you just subtract, you won't get any group. You subtract some subset, you won't get a group necessarily. Right? So you quotient by that. Another thing is this will be normal. So that also this will be normal in G that you can prove. And when you quotient by it, you've got rid of the commutativity, really. You should actually exist. And then this will always be abelian. So it's not you can't get an abelian quotient. You can always get a abelian quotient for any group. But the point is, when you divide by Z of G, if that is abelian, then it is nilpotent. In fact, that's particular case nilpotent of class 2. Okay. If it is non-abelian and you, so this is nilpotent group of class 2. So class also you can define based on how many steps you need to get to 1. So if it is already abelian, in 1 step you get to 1. That means nilpotent group of class 1 means abelian group. Nilpotent group of class 2 is like this. So it is not abelian, but its quotient is abelian. That one's quotient is of course trivial. So its quotient is abelian, not trivial. Okay. So non-trivial abelian groups, so that's class 2. Okay. And so you can define potence class. So that tells you how non-abelian it is. Right? How far away from an abelian group it is. So this is always abelian, but the particular case where this happens to be contained in the center, then it is nilpotent group of class 2. This is another way to say that. So if yeah, which is then oh sorry, not like that. If G is non-abelian, but G prime is contained in Z of G, then G is a nilpotent group of class 2. Okay, that means G is not abelian, but G mod Z of G is abelian. So actually, this more general than this. Uh, G mod N is so this is abelian if and only if G prime is contained in N. For any normal subgroup N of G, G mod N is abelian if and only if derived subgroup G prime is contained in N. Okay. So in particular, when G prime is contained in Z of G, G mod Z of G is definitely abelian. Okay, and so that will be class 2. Okay. Okay, I'll stop for this. Continue in the tutorials. Thank you. Yes.
Outside the participant, please collect your book.
Sorry. Yes, yes. Exactly. Yeah. So you can say that G prime is the smallest subgroup of G, such a question by any to get abelian group. Okay, that is good. What is it? Yeah, yeah, yeah. I know. I have. Wait. I have signed.